So it's my pleasure to announce Professor Marcelo Disconzi for our Rocky Mountain Mathematical Physics Seminar. Professor Disconzi is professor of mathematics at Vanderbilt University. He earned his PhD from State University of New York at Stony Brook. And his interests lie in partial differential equations, geometric analysis, and mathematical physics. He will speak today about the relativistic Euler equations with a physical vacuum boundary. Please.
So thank you, Marcus, for the invitation, the kind introduction, and thank you, the audience, for being here. Everything I'm saying today is joint work with Mihaela Ifrim and Daniel Tataru. So let's consider the beginning a fluid in a region that's not fixed, but is a region that can move with the fluid motion. So the picture is something like this. At time zero, we have a region containing a fluid. And as the fluid moves, it deforms the region that contains it. So at time t, the region looks different, something like this. So examples of this situation would be, for example, a liquid drop or a star. And fluids of this type, where the region moves with the fluid, they are called free boundary fluids. And right away, let me make a sort of little apology that the study of free boundary fluids is a wide and active field of research. So I cannot give credit to all the people who did important work in the field. When I do a literature review, I'm going to restrict myself to works that deal directly with the relativistic Euler equations, which is what we are going to be discussing here. So as I just said, if you have a free boundary fluid, then the region is not fixed, so it's not known ahead of time. So the region containing the fluid is itself a part of the unknown in the problems. It has to be determined alongside the fluid flow. So if you denote the fluid containing the region at time t by omega t, then the dynamics is going to be defined in this space-time region, which is simply the union over a time interval of all the omega t regions. And that's called the moving domain. So the picture would be something like this. At time t1, for example, we have the region omega t1. At time t2, we have the region omega t2. They are in general different. And then you take the union, and you get this region that's a cylinder-like region in space-time. And the fluid's free boundary is simply the union over this time interval of all the boundaries of this domain omega t's. The free boundary is also called the moving boundary or the free interface. They're all terminologies for signaling the fact that the boundary is moving with the fluid. And what is important to underscore here is that understanding the dynamics of the free boundary is essential in free boundary problems. That's precisely because that's what distinguishes this problem from a standard initial boundary value problem. In a standard initial boundary value problem, the domain is fixed. It would have time is zero. The dynamics is defined simply in omega 0 cross a time interval. So it's exactly the motion of the boundary is distinguished from this more traditional initial boundary value problem that we study in PD courses, introductory PD courses. Okay, so that's like the notion of a free boundary. So next, let me tell you about the relativistic Euler equations. The relativistic Euler equations, they describe an ideal fluid. Ideal means a fluid without viscosity in regimes where Einstein's theory of relativity cannot be neglected. So here are some examples where you want to use the relativistic Euler equations. If we have, for example, a fluid that's moving at speeds near the speed of light, that's what happens, for example, in the relativistic plasma that forms in collisions of heavy ions that are performed in particle accelerators, or in accretion disks near black holes. Another example is if you have a very strong gravitational field. That would be, for example, if you have a neutron star. So these are situations where you want to use the relativistic Euler equations or some other relativistic model, depending on the problem. So the relativistic Euler equations are written here, and I'm going to explain what all those symbols mean. Partial mu is simply abbreviation for the derivative with respect to x mu, and x mu from 0 to 3. These are coordinates in space-time. And I'm using the standard convention relativity that the x0 coordinate is singled out as a time coordinate. And then simply x denotes the spatial coordinates. Greek indices are always varying from 0 to 3, and Latin indices always vary from 1 to 3. And I'm using the sum convention that whenever you have a repeated index like this, it's summed over its range. Then in these equations, rho is the density of the fluid, and u is the velocity of the fluid. So sometimes we call it the Ford velocity to emphasize the fact that in relativity, the velocity, it's not a vector field in space, but it's a vector field in space-time. So it has 4 components. And they are, of course, both functions of time and space. P, that appears here in the equations, is the pressure of the fluid, and P is a known function of the density, given by what is called an equation of state. And which equation of state you choose depends on the nature of the fluid, depends on the problem you're studying. And I'm going to fix an equation of state later on that we're going to consider for this problem. G is the Minkowski metric. We can study this problem with any given Lorentzian metric, but all the important conceptual issues and technical difficulties are already present if you consider Minkowski metric, so we just stick to that for simplicity. And pi is the projection onto the orthogonal space to the velocity. So these two first equations, they represent the conservation of energy and momentum in the fluid. Then have this third equation that you see it has no derivative, so this is a constraint. And the way you should think of this third equation is a constraint that's propagated by the flow. You have this normalization condition on the velocity, saying that the velocity square with respect to the Minkowski metric is -1. And if that holds for initial data, and you have a solution to these first two equations, that holds for later time. And of course, remember that the Minkowski metric is Lorentzian. So for a Lorentzian metric, for a Lorentzian metric, you can have that the norm square is negative, right? It's not Riemannian. It's not positive definitely. And what you want to do, you want to study these equations, but in the setting that was described before, where the fluid, the region containing the fluid is moving with the fluid. So you want to study the relativistic free boundary Euler equations. Now, because you have a boundary, you need to find correct boundary conditions, and the correct boundary condition for this free boundary problem that comes from physics, it's that the pressure has to vanish on the free boundary. But as I just told you, the pressure is given in terms of the density by an equation of state, so this condition can be reinterpreted as a condition for the density on the free boundary. Now, there's an important distinction that I need to make. And it depends on the problem you're studying, depends in part also on the equation of state, which is the following. If the density, whatever condition you have on the boundary, but it is such that it is bounded away from zero, from below away from zero, then you say that you have a liquid. And if the density vanishes on the boundary, you say that you have a gas. In both cases, the pressure vanishes on the boundary, but then you have this distinction of whether the density vanishes or not on the boundary. And I think the names liquid or gas are more or less self-explanatory. And what is important to remark is that the liquid and gas cases are very different problems. So they involve different techniques, different physics. So here we're going to pick one of them. And in this problem, we're going to study the case of a gas. Okay, we're going to focus on the case of a gas where the density vanishes on the boundary. That's a boundary condition that you also have. And in this case, we also call the free boundary a vacuum boundary. So the model you should have in mind here is really like a star. You have a fluid inside a region, in a vacuum outside, but this star is a gas, which means that when you approach the boundary, the density is really vanish on the boundary. That's the physical model you should have in mind. Now for a gas, the moving domain at time t that I was depicting those pictures can be simply characterized is simply the set of points for which the density at time t is positive. So that's the moving domain at time t. There's another boundary condition, which means that the velocity has to be tangent to the free boundary. So the forward velocity has to be tangent to this set in space-time, but that boundary condition is kinematic in nature, so I'm not going to say much about it. I'm going to downplay the role of the second boundary condition. You can view it more like as a consistent condition for the problem. Okay, so the one quantity that's going to play a key role in this talk is the fluid sound speed, which is defined as follows. The sound speed square is the derivative of the pressure evaluated of the density, at the density, and therefore the sound speed square is a function of time and space. And we call this the sound speed because it really corresponds to the speed of sound waves in your fluid. There are different ways of seeing this. For example, you can compute the characteristics of the Euler system. And if you do that, you're going to see that one of the characteristics, they have the form of cones in space-time. So if you have cones in space-time, it's very much like when you have the light cones for the wave equation. And in the case of the standard wave equation, you interpret that as propagation of light. But these cones, you interpret as propagation of sound in your fluid. And these cones that appear when you compute the characteristics, they have an opening that corresponds precisely to this quantity Cs. So that's how you know that this is the sound speed of your fluid. Now, in this problem of the gas, that's not the case for the liquid, but for the gas, we also demand that the sound speed vanishes on the free surface, on the boundary. And this is essentially saying that if you have a region where the density is vanishing, so there is no medium for your sound to propagate, so you cannot have sound waves propagating across the boundary into vacuum. And then it turns out that the vanishing rate of the sound speed square near the free boundary plays a crucial role in this problem. Essentially, there is only one natural decay rate which is consistent with the time evolution. And the decay rate that is consistent with the time evolution is that the sound speed square is comparable to the distance to the boundary, at least for points near the boundary. Away from the boundary, you don't need to require this. And this condition is known as a physical vacuum boundary condition. So that's the title of my talk. I do the relativistic Euler equations. So you're taking the Euler equations with a free boundary, but in the case of a physical vacuum boundary, we're looking at problems where the sound speed square has to satisfy this condition. And the way you should think of this condition is pretty much like a constraint that's propagated by the flow, which means we impose this condition on the initial data, and then you show that when you have a solution for a short time, this condition still holds for a short time if to hold the time zero. Now, you might be wondering why I say that there is essentially one natural decay rate, which is this one. That's because if you have a faster decay rate, that would cause the boundary to simply move independently and linearly with the outer particle's speed. And that's not very physical, because if you have, like, again, if you have something like a star, for example, the boundary is in particular accelerating because the star is rotating and so on, right? And if you have a slower decay rate, that gives a very similar problem, likely causing an infinite initial acceleration of the boundary. So that's really the decay rate that's consistent with what we expect from the physics. Now, this physical vacuum boundary condition, that the sound speed square is comparable to the distance to the boundary, in particular implies that if you look at linear waves with this sound speed, they reach the boundary in finite time. Therefore, the motion of the boundaries is strongly coupled with the wave evolution, and it's not just a self-contained evolution leading order. Now, if you haven't seen free boundary problems before, that statement might look out of place here, but I'm just pointing out this because in many free boundary problems, you can sort of view the evolution of the boundary more or less as self-contained. But here, the evolution of the boundary is strongly coupled to the evolution of the fluid in the interior. And another feature of this problem is that the relativistic Euler equations with a free boundary in the case of a gas, they degenerate on the boundary. So if you go back to the equations, you see you have this term, the pressure vanishes on the boundary, and for a gas, the density vanishes on the boundary. So this term disappears, drops out of the equation on the boundary. The same thing with this term, which means that the equations degenerate on the boundary. Okay, that's not the case for a liquid. If you have a liquid, then the density is bounded away from zero, and these two terms, they are present even when you approach the boundary. That's just one hint of how the liquid and gas problems are very different. Now, we need to fix an equation of state. So the standard choice in the state study of the relativistic Euler equations with a physical vacuum boundary is a power law for the density. So we're going to choose the pressure to be a power greater than 1, and for convenience, this power greater than 1, we're going to write as kappa plus 1, where kappa is greater than 0. So from now on, we're going to assume this equation of state for the rest of the talk. Okay, so let me just kind of give you a sort of very high-level outline of the main ideas that we're going to use in the proof of local well-posedness for these equations. The first step involves finding some good nonlinear variables. And by good nonlinear variables, you mean rewrite the system in terms of certain variables that are going to diagonalize the system with respect to the material derivative. The material derivative is this vector field, which the time derivative plus the derivative in the direction of the spatial component, the spatial part of the velocity, with a suitable normalization where you divide by the zero component of the velocity. Remember, the velocity has 4 components, and I represents this is a Latin index. Latin indices range from 1 to 3, which denote the spatial components of the velocity. Now, if you don't know fluids, you might be wondering what this material derivative means. It turns out that it is this combination of time and spatial derivatives that's really the relevant quantity for tracking the evolution of fluid particles in our fluid. So the dynamics is tied to the material derivative and not so much just to the time derivative, as you would expect in a regular initial boundary value problem. And because it is this derivative, the material derivative, that's really tied to the dynamics of the fluid particles, you want a system that's going to be diagonal with respect to the material derivative. So you want to diagonalize the system in that form. Then the second step is going to be to choose some good linear variables. So the analysis of the linearized equation plays a main role in our approach. And you have to write the equation in terms of some good variables to carry out the analysis. And then what you're going to do, you're going to derive some energy estimates for a certain number of material derivatives of your good nonlinear variables. And what you want to show is that this quantity material derivatives of the good nonlinear variables, they actually satisfy the linearized equation with some error terms, which are going to be good perturbative terms. Now, when you derive such estimates, these are going to be estimates for material derivatives of the nonlinear variables, and you want to control all the derivatives to do standard estimates. So you connect these estimates with full derivatives using elliptic estimates. And finally, to construct solutions, you're going to use a regularization and a time discretization. Okay, so this is kind of very briefly kind of the outline of the main ideas, and I'm going to discuss them in more detail as the talk goes. So let me start telling you about these good nonlinear variables. So what you're going to do, we are going to rescale the velocity by a certain function of the density, which is going to be chosen properly. So we introduce this new variable v, which I'm going to continue to call the velocity, which is this multiple of the density. And if now you use the original equations to write an evolution equation for v, you get this equation here. Okay. Now let me point out that here I'm already writing evolution for the I component of v, which means the spatial components. It suffices to write the evolution for the spatial components because using the normalization, you can always write the zero component in terms of the spatial components. And this term here is good because this term involves, you see, this term u contracted with the partial derivative up to some coefficient here. This is exactly the material derivative, which is what you want. So it's a multiple of the material derivative. And you want to be diagonal, so you don't want any other term to have the material derivative. This term here is fine because even though you are summing over mu, This is the Minkowski metric, doesn't have any off-diagonal term, so this involves only spatial derivatives. But this term here involves the material derivative. In particular, involves a time derivative here when you sum over. So you want to kill this term. The way you kill this term is by making this parenthesis vanish, and you do that by simply choosing f, which I haven't chosen so far, such that this term is 0. And so if that set is equal to 0, you solve this ODE for f, and you find that f has to have this expression. Okay, that kills the bad term that you don't want. However, if you have ever worked with the relativistic Euler equations before, you look at this expression, you immediately recognize as something. This expression for f is precisely what you use to define the vorticity of the fluid. It turns out that in relativity, the vorticity is not defined simply as the curl of the velocity, like you do for ordinary, for example, in compressible Euler equations, but is the space-time curl, which means the exterior derivative, and not of the original for velocity u, but of a multiple of u, and this multiple turns out to be exactly this function here. So at this point, you imagine you're on the right track, because the function that you chose without thinking about the vorticity, just to kill this term, turns out to be exactly what you used for the vorticity. And then a calculation shows the vorticity satisfies this evolution equation, which is a transport type of equation for the vorticity. Okay. Now you can also show with the definition that the vorticity is actually orthogonal to the velocity. So you have this orthogonality condition, and you can use this orthogonal condition to re-express this equation as an equation involving only the spatial components of the vorticity. That's because, as I said before, you want to deal only with the spatial components of the velocity. So you want to write everything in terms of only the spatial components, and you can do that using the orthogonality of the vorticity in the velocity. Okay. Now, at this point, I make an important remark. Everything I'm going to say from now on has to be complemented with estimates for the vorticity. And estimates for the vorticity, they are obtained directly from this equation by using standard estimates for transport equations. But I'm not going to mention that. Okay, so that's everything has to be complemented with estimates for the vorticity. But for the rest of the talk, I'm going to forget about the vorticity and just talk about the other equations that are more delicate. Okay, estimates for the vorticity, they follow directly from this equation. Now, the change of variables that I mentioned, it also diagonalizes the equation for the density. You get to this equation here, right? Don't worry too much about the details. And I point out that the equations, they're actually a little uglier than what I wrote here. There are several coefficients which are of order 1, which are not very important for what I'm going to say. I'm going to omit all these coefficients just so that the equations that I'm going to write down, they don't look very complicated. Now, everything that I just told you is for an arbitrary equation of state. So for the equation of state that we want, which is this power law, the velocity takes this form. And then it's convenient to work not with the density, but work with this certain, with the power of the density, with this multiple here. And for this equation of state, if you look at this quantity, except for dividing by kappa, this is precisely the sound speed square, but it's convenient to divide by kappa. So I'm going to take as my variables now to be v and the sound speed square up to a factor, but I'm going to continue to call the sound speed square. And then in this case, the equations take this form, this simple looking form, where this capital G now that appears when you write down the equations is given by this quantity, and this because of the condition they have for the normalization, that the velocity square, the u square is -1, v0 square is going to be something else, but because of that condition, this turns out to be positive definite. So this is a Riemannian metric now that you have in this equation. So in particular, because this is a metric and you have here the derivative of the components of the velocity, this term is precisely a divergence operator. The divergence operator, but it's not divergence with respect to the Euclidean metric, it's divergence with respect to this other metric here. Now, the fact that this G appears, if you have seen the relativistic Euler equations before, it's not so surprising. This metric turns out to be related to something called the acoustical metric. And the acoustical metric is another Lorentzian metric that appears in the study of the relativistic Euler equations, which is the Lorentzian metric that's exactly tied to the propagation of sound waves. Whenever you have waves, there is some metric structure, some Lorentzian metric lurking behind. And in the case of sound waves, that's called the acoustical metric. And this G is related to that. So it's not so surprising that this G appears. Now, if you look at these equations, and if you're a fluids person, you might think they look kind of quite reasonable. You have a divergence, that's common in fluids. You have the material derivative, but you have this last term that appears like something we never see in fluids. So in my word, this last term is going to cause trouble, this term here. Now, it turns out that this term can actually be treated as a perturbation in a certain sense. To see this, imagine you're deriving estimates for this equation. So what you're going to do, you're treating the differentiated R as the variable you're estimating, the second R as a coefficient. So let me call the differentiated guy by S. You're going to multiply this equation by S, and then what you get is you get a perfect derivative which can integrate by parts. So you can end up with some standard estimate of the L2 type for this. So this last term, we're going to be able to treat essentially as a perturbation, even though it's some term that looks very different than what you see in fluids. Okay, so now I have the equations. So these are the equations that we're going to use. So the next thing that I need to define some function spaces. And the function space we're going to define, they're based on an energy that is admitted by the linearized equation. So if here, let's think of S as the linearized variable associated with R and W as the linearized variable associated with V. And then you can show that the linearized equation, they admit this energy. So here, of course, you're interested in the case of R is the actual R in the problem, the sound speed square. But you can think of this norm in an arbitrary domain, which is given by a defining function R, which means a function whose distance is comparable to a function that's comparable to the distance to the boundary near the boundary. Okay. Now, you see this energy, so this norm is what? Is a L2 type of norm, right? So you have S squared, you have W squared, but this is squared with respect to this metric, and you have certain weights, right? So these R's are like the distance to the boundary, so they're like weights. So this is a weighted L2 norm. That's why you should think of this basic norm here. And then whenever you have your basic L2, what you want to do in this type of problems, you want to define some higher order norms. And the question is that how to define the higher order norms in this problem. For that, we look at what happens to the wave evolution, the evolution of the sound waves. So the wave evolution is governed by an operator that has this form, which is like a wave operator, but it's a wave operator involving the material derivative instead of the time derivative. And instead of a Laplacian, you have a degenerate operator because it's R times the Laplacian. Now, your norms, in principle, you want to construct things that involve only spatial derivatives. So that suggests construct norms based on powers of R times the Laplacian. So we're going to introduce these higher order norms, which are given by these very early expressions. So don't pay too much attention to all these indices. Let me just highlight what's happening at the highest order in these norms. So if you look at the highest order, so here you have a term that involves k powers of R times 2k derivatives of S. That's precisely what you get if you take R times Laplacian to the power k, right? It's R to the k and 2k derivatives. And then you have some extra weights. So these extra weights are coming from the fact that you're building this norm on top of this basic weighted L2 norm. The same thing for W, right? You have like R to the k times 2k derivatives, which this guy to the power 2k, with some extra weight that's coming from this weighted L2 norm. And notice that you have an extra factor of half here because this norm in the W component has an extra factor of R here. Okay, so that's how you construct these norms. And now that I have my function spaces, those are the function spaces we're going to use to treat the problem. One thing that we do in PD, we do a scale analysis and try to identify if we have something like critical spaces. Now, to do the scale analysis, I'm going to start with my equations, and I'm going to ignore everything that's an order one term. So, for example, this G, which involves the Kronecker delta, but involves some v's. I'm going to throw the v's away. This material derivative involves vi divided by v naught. I'm going to throw v naught away. So everything that's order 1, I'm going to throw it away for this scaling analysis. And if you believe what I said before, this term can be treated as a perturbation. I'm going to throw away this guy as well. So if I do this sort of heuristics, I end up with these simpler equations, which I expect they are capturing the leading order dynamics of the motion, of the fluid motion. And now the simplified equations, they admit some scale symmetry. They have the following scaling law written here, which means that if you rescale your quantities in this form, you take solutions into solutions. And now that you have this scaling law, you can define some critical spaces. So our critical spaces are going to be the spaces age 2k that I introduced before, where 2k is exactly equal to this quantity here. Okay, and I'm highlighting 3 here because 3, as it goes in this kind of scale analysis, 3 is the dimension of space. You can do this in any number of spatial dimensions, and in fact, in the paper we do this for an arbitrary number of dimensions. But here I'm considering only the physically most important case, which is when this number of spatial dimensions is 3. Okay, so then you have these critical spaces. Okay, now I have all the ingredients that I need to state the first theorem, which is the local opposingness. So we define this configuration space, which is the space of RV functions, such that for each time they belong to this weighted space that I introduced before. Think of this as some weighted Sobolev spaces. So these are our configuration spaces. And the statement is the following. So the relativistic Euler equations with a physical vacuum boundary, they're locally well posed in these age 2k spaces if the following is true: if the initial data has the same regularity, and if the physical vacuum boundary condition is satisfied for the sound speed square times 0. Remember, I told you that the way you see the physical vacuum boundary condition is something to impose on the initial data, right? Moreover, the regularity is not arbitrary, but you need to have regularity which is half degree above scaling, right? So remember, you have this critical scaling k naught. So this inequality is telling that this is going to hold when k is greater than k naught plus a half. Okay. And by local opposingness, I mean local opposingness in the usual sense, means local existence of solutions, local uniqueness, and continuous dependence of solutions on the data with respect to the topology in this space, which is given by these norms. Now, the topology of this space is a little more complicated because, remember, for each time these domains are moving, but you can define what the topology of this space is. Okay, so that's the first result. And the next result that I'm going to state is the result about a continuation criteria, when we can continue the solutions. You have the solution up to a certain time, open the open interval in time. Can you continue past that end point in your time interval? But to state that, first I need to introduce some more norms. Okay, so I'm going to, so those are, we call control norms, A and B, given by these complicated expressions, which I'm going to explain what they mean. So first, here you have this L-infinity norm involved this quantity n. And n is the following. N is a given vector field with the following property. If you fix some point on the boundary, n at that point is exactly equal to the gradient of r at that point. And you can do this in a collection of points around the boundary. And the idea of introducing this n is because by localizing the problem and work in a sufficiently small neighborhood of this point x naught, you can make this quantity very small. Now, if you don't have this n, if you're just looking at the gradient of r in L-infinity, then this quantity cannot be made small by localization or scaling arguments. And for reasons I'm going to explain later, you want to be able to make this quantity here small. And then you have the second norm B, which involves A, but involves this other quantity, which I'm calling C tilde and a half, defined here. So again, this is complicated, but the way you should think of this is essentially like the Holder semi-norm 3/2, right? Because you're looking at a gradient divided by x minus y to the half, except that this actually is slightly weaker than the Holder 3/2 norm, because it involves only one derivative away from the boundary, because away from the boundary, R is actually non-zero, right? In terms of the previous function spaces that I introduced, this quantity A is associated with the critical space because you have this embedding that the H2K norm controls this norm A for K strictly greater than K naught. And this space, this norm B is associated with the critical space plus a half, because you have this embedding saying that the 2K norm controls B if 2K is greater than 2K naught plus 1. Okay. So then I can state the next theorem, which is the following. For each integer k, there exists an energy function of e to the 2k, or e2k. It's a function of R and V with the following properties. First, we have coercivity, which means that as long as A remains bounded, this function is in fact equivalent to the H2K norm square. And second, we have energy estimates for solutions, which means that the time derivative of this functional is controlled by the H2K norm square with a factor that's linear in this norm B and with a second dependence in this norm A. Then from these two facts, you can just Grunwald this inequality and say that you can control your norm at time t by the norm at time 0 in the initial data with an exponential factor that involves this norm B. So this tells in particular that solutions can be continued in time as long as A remains bounded and B is integrable in time. Okay, so this is like this looks like very much like a standard continuation criteria that you have for the ordinary Euler equations without a free boundary, and for many other PDEs, in fact. Okay. So those are the theorems, and I want to give you then an idea of how these things are proven. But before, let me just give a brief overview of the literature. And even though we're not talking about the case of a liquid, just for context, let me tell you also what is known about the liquid. For a liquid, a priori estimates were obtained by Olynyk and Ginsburg. And then local existence uniqueness were obtained by Olynyk and also by Miao, Shashahani, and Wu. And this later result is for the fluid in what is called a hard phase, when the sound speed is equal to 1, and my units 1 is the speed of light. There's also an approach using first-order symmetric hyperbolic system due to Trakinin. In this paper, what it does is solves the problem for the non-relativistic or compressible Euler equations, and then he kind of sketches how those arguments could be adapted for the relativistic setting. So in sum, there is good progress recently in the case of a liquid. If you have a gas, but under symmetry assumptions, that several things are known. The first result actually goes back to the 30s in the work of Tolman, Oppenheim, and Folkoff. So that's here they build the first model of stars. Those are spherically symmetric static solutions to the Einstein-Euler system. And it is in this paper that they identified that the pressure eventually the boundary is the correct boundary condition for the problem. Then spherically symmetric static solutions of the Einstein-Euler system obtained by Lindblom, Rendau, and Schmidt, and Makino. Makino has some further results where he has solutions near equilibrium in spherical symmetry. Equilibrium means solutions to the TOV equations. And he also extended that to axis symmetry for slowly rotating stars. There are further results by Hailing, Makino, and quite recently, Hadzik and Lin, they proved what's called the turning point principle for relativistic stars. So the message is that quite a few things can be said if you work under symmetry assumptions, and in this case, you are including even cases where you couple to Einstein's equations. Now we can look at a gas without the physical vacuum boundary condition. That, as I said, is not very physical, but we can still study mathematically that. And in that case, the problem was solved by Rendau, McKean and Yukai, Lefloc and Yukai, Brouwer and Karp. Although in this case, because you don't have the physical vacuum boundary condition, there are some unnatural regularity assumptions that come into play that have to do with the fact that the fluid does not accelerate on the boundary. And there's a frame formalism introduced by Friedrich, but as far as I know, that has not been turned into a full proof of local opposingness for this problem.
Just a question here. So that's Helmut Friedrich?
Yes.
Okay.
So the punchline is that you can have a few results if you violate the physical vacuum boundary condition. And finally, in the case we're studying, relativistic Euler equations, the case of a gas with a physical vacuum, a priori estimates were obtained by Young, Lefloc, and Masmoudi, and Hadji, Scholar, and Speck. And for people who know fluids, I point out that these results, they are all in Lagrangian coordinates, and this is in contrast to our approach, which is entirely in Eulerian coordinates. And there is one local existence unique result due to Euler-Unique, but that's in 1 + 1 dimension. Now, in 1 + 1 dimension, the boundary is just points, so the geometry does not play any role, so the main difficulties are absent in that case. Okay, so as you can see, there was no local existence and unique result for these equations prior to our work. So that's our contribution to this list. So now let me, how much time do I have, Mark? So like 10 minutes?
Yeah. So we started almost 5 minutes later, so you have 10 minutes, that's fine.
Okay, so in the remaining time, let's just give a few highlights of the proof. Let's look again at the linearized equations. Again, think of S as the linearized variable associated with R, W associated with V. So the linearized equations are written here. Everything's not important, I'm calling an error, moving to the right-hand side. And as I mentioned, this linearized system admits an energy given by this weighted L2 norm. Now, there is this term that's not present in the original equations, and this term comes from the fact that when you linearize the equations, remember the material derivative involves the velocity. So when you linearize that term in the material derivative, this guy pops out. And at first sight, this involves no derivative of the linearized variable, right? So this is a linearized equation. So you think of S and W as the variables, and everything else as a coefficient given to you. So you'd think that this term is an error because it does not involve derivatives of W, but turns out that this guy is important, it's not an error. And to explain that, let me set kappa equal to 1 for simplicity. And then what you're gonna do when you do energy estimates, you're gonna multiply the evolution equation for S by S, and you multiply the evolution equation for W by W. And you do that for reasons that I'm going to explain in a second. You multiply the second equation not only by W, but by W with this coefficient. It involves G and involves R. And then these terms with the time derivatives, the material derivatives, after integrate by parts, they produce precisely this energy that you get here. Okay. However, when you do this multiplication, you get some cross terms. You have here S times this term, and here you have W times this term. So these cross terms, you have to deal with them. So the first observation is because this cross term here involves R and G. That's why when you multiply the W equation, you also don't multiply only by W, you multiply by W weighted by R and G. But more importantly, you need to cancel out these cross terms to control your energy. Otherwise you cannot close your estimate. So for that, you have to do an integration by parts, but you don't get a cancellation unless you keep this term here, you keep track of this term, because when you do integration by parts, there's going to be one term, right? You combine these two terms with the product rule, but there's one term when you integrate by parts that's going to, a derivative hits the coefficient R, and that's comes as a minus sign and cancel with this term here that came from the linearization of the material derivative. Now, all that I just said might sound a bit technical. So if you're not familiar with energy estimates, all you have to keep in mind is that this term is important for some cancellation that's going to play a role later on. And then once you have your basic estimate, what you do in PDs, you want to take derivatives of the equation, and apply the same kind of argument. But you run into a problem, because when you start differentiating this equation, you have terms where the derivatives hit these weights R. But you need the weights in your norm. This is a weighted problem. Your norm is a weighted norm. So, so you want to kill the weight structure of your problem if you just take the derivative of the equation. However, if instead of arbitrary derivatives, you take material derivatives, every time that your material derivative hits the weight R, you get the weight back. That's because if you look at your equations, dtr is always equal to R times something. Okay, so you always get the weight back. So that says that you should differentiate the equation only with the material derivatives, or at least suggests. Okay, so the idea is to work with material derivatives of the variables R and V, and you hope that these material derivatives are going to solve the linearized equation with good perturbative terms, because for the linearized equation, you have the basic estimate that I just mentioned before. However, this is not quite true, because the material derivative does not generate an exact symmetry of the equation like an ordinary derivative, right? So that important term for the cancellation comes precisely from the fact that you linearize the equation. But if you just take a material derivative commutes with itself, so it does not produce that term that's important for the cancellation. So what you do, you introduce some new variables that we call the good linear variables, which are precisely what you want, the material derivatives of V and R. So here I'm taking n material derivatives, so I'm indexing these variables by n, but I subtract by hand that term that I need for the cancellation. And the idea that these variables S and W, they are with the S and W subindex n, they are good approximations for solutions to the linearized equation. And then for the linearized equation, I know what the energy is, so I can construct this energy, which is simply the sum up to the order k that I want of all the linearized variables using the basic L2 weighted norm. Okay, so here this index 2n tells you that you are taking up to 2n the material derivatives. But in the end, as I mentioned, you want to have estimates for the full derivatives, not only material derivatives. So if you recursively solve for the material derivatives in terms of spatial derivatives, you observe some kind of structure that 2n material derivatives can be traded essentially by 2n spatial derivatives with a weight r to the n. So you want to make this, this idea rigorous, and you notice that this structure r to the n times 2n derivatives is exactly what appeared in the norm that I was mentioning before. So you can start seeing how all these things start coming together now. Excuse me. Okay, so to actually prove that you can do this, you can trade material derivatives by spatial derivatives with the correct weight. What you're going to do, you're going to use some elliptic estimates for these operators L1 and L2. We call these transition operators because what they do, they connect the variables at the level 2n with the variables at the level 2n minus 2. Remember, 2n means 2n material derivatives, 2n minus 2 means 2n minus 2 material derivatives. They are connected by applying to operators L1 and L2 up to some error terms. Now, these operators, they come from the wave evolution. Before, I told you the wave evolution was material derivative square minus r times the Laplacian, but I was lying a little bit. They're actually, it's not exactly the Laplacian, it's something more complicated. It looks like a Laplacian, but is actually given by these operators L1 and L2. Those are the operators that appear in our wave evolution. So that's where these operators L1 and L2 come from. And then we can prove some elliptic estimates for these guys. The elliptic estimates, they're, well, like regular elliptic estimates, the variables where you apply the operators, which means the variables at the level 2n minus 2, they are bounded by the variables at the level 2n, always with a gain of 2 derivatives. So if you iterate this inequality all the way to the top level, you can get a bound for your variables, for your full variables now, because now this involves the spatial derivatives, the norms, up to an error term. And this error term appears because of these terms f and g. and you can prove an estimate where f and g are bounded by the norm that you want with a term that involves that norm A. And here's where you use the fact that norm A can be made small by a localization argument. So that's why you get an epsilon. So when you iterate this guy, this inequality, you can absorb this on the left-hand side by taking epsilon small. Okay, so this gives the coercivity of the energy, right? So the energy controls the norm. The other inequality is not so difficult. So you can, that's how you get the equivalence of the energy and the norm. And then you can finally establish energy estimates. And the energy estimates you establish again by using the good linearized variables and using the fact that it satisfies the linearized equation with some good perturbative terms, except that good perturbative terms in this slide has a different meaning than in the previous one. What good means is that we can always treat these perturbative terms by interpolation, always with a single factor of B, because you want the inequality to be linear in B to get the continuation criteria. Okay, so all that I just told you is about just estimates. So now how actually go from estimates to actually construct solutions? Well, for that, we're going to use a time discretization. And this time discretization is going to be, this is going to be done in steps. So we're going to have a regularization involved. This regularization is quite technical, but it's not surprising that you have to use a regularization. This is kind of something that appears when we prove like this kind of theorems of existence for PDEs. There's a transport part to the construction of solutions. By transport, I mean that I'm discretizing in time, and then each time step, I have to not only get the new variables, but also have to move the domain, because remember, the domain is moving. And finally, there's a Newton's method involved. Now, what is very interesting here is that all these steps taken separately, they are unbounded. It means you cannot control, you don't get good control from your discretization. But when you take these steps together, there's an extra cancellation that comes to rescue. And this extra cancellation is the direct analog of that cancellation that I told you before for the linearized equation. So it's the same kind of structure appearing here in a different form. And finally, you're saying, okay, but hold on, all your estimates, right? You want to use your estimates to be able to pass to the continuous limit because you're discretizing time. But your estimates, you are using time derivatives. So you're using a continuous time. So how can you use your estimates for this time discretized problem? And what you do here is that you can reinterpret these operators as purely spatial operators by using the equations to solve for the material derivatives in terms of spatial derivatives, similar to what I mentioned before. And in that case, you can get the estimates because you have a uniform control of these norms. You can pass to the continuous limit and obtain solutions. Okay, so that's the existence. I'm running out of time, so let me just say that we can also prove uniqueness. And the uniqueness is quite interesting because this is a uniqueness done in Eulerian coordinates. So if people who know about it they can ask later. Mm-hmm. And of course, the story doesn't end here. Now, we have this proof for, as I said, is the first proof for local opposingness for the relativistic Euler equations with a physical vacuum boundary, and that opens the door for other models. You can include entropy. You can look at expanding gases. That's something that in the classical case was done by Young, Hadzik, and Rickard. We can look at non-relativistic limits, other models, and if you are really ambitious, you can look at this problem for the Einstein-Euler system. Thank you for your attention.
Yeah, let's thank the speaker for the nice talk. Are there questions?
I guess I'm curious about the function spaces. Could you go back to the slide when you define them, please? Yeah, so, or maybe after this. Yes, the powers of the Laplacian.
Yeah.
Yes. So I'm curious because, okay, so R is one of the unknowns, yes?
Yeah, but of course, this space you can define. You can define for a given R that has the property that is like the distance to the boundary near the boundary, and the domain is R greater than 0, right? So for the constructive solution, we are always taking R from the previous step because we're doing this iteration, right?
I see. Ah, very nice. Okay, okay. I see. Okay, because I got confused with the arrows R2SV. Okay, but okay, that makes perfect sense. Very nice. Very nice. Okay, thank you. That was my question. Yes. So, and okay, I guess, okay, last thing. So the first step, you would just plug in the initial data, and it's just the fact that it depends on space, it's enough, right? There is no, okay.
In fact, okay, morally that's it, but of course there is this regularization step. So it's not exactly the initial data, it's a regularization that is involved, right? And then of course this regularization has to be done carefully because you see, when you regularize things, you do like a modification, right? But if you're at the boundary, you have to modify by, you cannot modify at the boundary, because then if you take a ball on the boundary, you're going to be outside the boundary in some parts, right? So you have to kind of adjust these things with some precise boundary layers. But morally, that's it. At the type 0, you put the initial data, but it's actually a regularization that you put.
Okay. Thank you.
Further questions? I have a question, maybe that is a bit far-fetched, but we are here. I mean, Daniel and Agnes and myself, we are, I would say, quantum people. And so is there some way to bring quantum in here, a quantized version? I mean, connecting quantum theory with relativity is a huge problem, so I don't expect a full answer here. But there are ways of connecting it somehow, and anyway, so maybe you can just tell a bit on this.
Yeah, okay. As far as I see, not so much with like the PDs themselves, but one way that quantum theory certainly has to appear is in the choice of equation of state. So this is like a model, right? It's a model, right? That's equation of state. For example, if you look at the equation of state that people, there are different equations of state that people use in star evolution, right? And I was saying that star is like the primary motivation for this kind of problem. One thing that we know is like, for example, when you look at the fact that the star is not collapsing under its own gravity, one factor that's preventing this collapse is actually the Fermi pressure, right? They have the exclusion principle, right? So they have like this electron degeneracy, right, that's causing a pressure that contributes to the fact that the star is not collapsing in its own gravity, right? And I hope I use the terminology right, but that's the mechanism, right? So, and that's of course a quantum phenomenon, right? So that's an example of a quantum phenomenon that you actually have to include in the model to have the star not collapse under its own gravity. Now, the way that astrophysicists deal with that, they sort of know that's included in how they choose the equation of state, right? But if you go back to the microscopic dynamic, to kinetic theory and quantum kinetic theory, that's a factor that you have to include in your kinetic theory when you derive the equation of state from kinetic theory. So indirectly, there is some essential, I would say, quantum element appearing here in the equation of state. And again, this equation of state, it's good enough for a first approximation, but we know that the equation of states of stars, and in particular neutron stars, which is one example where you definitely have to use relativistic fluids, it's much more complicated than that. In fact, for neutron stars, the equation of state it's basically unknown, right? People don't know what the equation of state is, and if you derive things from kinetic theory at some point, you might likely have to include some quantum effects there.
Okay, thank you. So let's thank the speaker again.
Thank you.
And our next meeting will be in 3 weeks. Okay, thank you.
Thank you. Bye-bye.
Thank you. Thank you.